Hello and welcome to our fourth lesson. This week we're going to be talking about vectors and then using vectors to talk about the dot product of two vectors and the cross product of two vectors. First we'll discuss vectors. For some quantities, for example mass or time or distance, we only need a number to describe the quantity. But for some quantities, for example velocity or force, we need both a number and a direction. And this is what we use vectors for. A vector is an object which has a size and a direction. We can think of a direction as an arrow. The length of the arrow tells us the size of the vector, and the direction that the arrow points in gives us the direction of the vector. We might call a vector AB. This is a vector which has a starting point or initial point A, and it finishes at a terminal point B. If we want to talk about the length of the vector AB, we use these two vertical lines. Two vertical lines, AB, two vertical lines. We say that two vectors are equal if they have the same length and the same direction. Doesn't matter if they have different initial points or different terminal points. All we care about is the length of the vector and the direction of the vector. So for example, in this picture, the vector AB is the same as the vector CD because the directions are the same and the lengths are the same. The vector EF and the vector OP are also the same vector. However, the vector AB is not the same as the vector GH because the lengths are different. And the vector AB is not the same as the vector IJ because the directions are different. Before I go on, let's talk briefly about notation. When we use a computer to write vectors, we use bold letters for vectors. For example, bold U, bold V, or bold W. When we use a pen, when we're writing on paper or writing on a whiteboard, it's difficult to write bold, so instead we use underlined. Underlined U, underlined V, or underlined W for vectors. So for example, if when I'm typing, I write AU plus BV, U and V are in bold, so we can immediately say U and V are vectors. A and B are not in bold, so A and B must be numbers. Or if I write using a pen, or if you write your exam answers, A underlined U plus B underlined V. Again, U and V are underlined. U and V must be the vectors. A and B are not underlined, so A and B are numbers. If we're in two dimensions, if we're in R2, and if a vector V has initial point, the origin, 0, 0, and terminal point V1, V2, then we can say that the component form of V is V1, V2. We can do the same thing in three dimensions. If we're in R3, if the initial point is the origin and the terminal point is V1, V2, V3, then we say that the component form of V is V equal to V1, V2, V3. For example, here's a picture of a vector in three dimensions. Remember, we use the left hand to describe the positions of the vertices. X-axis using our second finger, the y-axis points in the direction of our first finger, and the z-axis points in the direction of our thumb. Suppose we have a vector which goes from P to Q. Initial point P, terminal point Q. In other words, we have the vector PQ, or we can call this the vector V. Then we can write that V or v1, v2, v3, is the same as x2 minus x1, y2 minus y1, z2 minus z1. We can talk about the length or the norm of the vector. If v has component form v1, v2, then the norm of v, or the length of v, remembering we use these vertical lines, is the square root of v1 squared plus v2 squared. And in 3 dimensions we have a similar formula. The norm of v is the square root of v1 squared plus v2 squared plus v3 squared. And from the previous picture, that was the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. The 0 vectors, that's the vector 0, 0, or 0 in bold, or in 3 dimensions, the vector 0, 0, 0, which we can write using bold 0, or with a pen underlined 0, have norm 0. You can see this from the formula. The square root of 0 plus 0 plus 0 is 0. Any vector which is not the 0 vector must have strictly positive norm. We can see this from the formulae. As long as at least one of v1, v2, and v3 is not 0, then v1 squared plus v2 squared plus v3 squared must be a strictly positive number, because squaring a negative number is a positive number. And then we square it, still we have a strictly positive number. For example, find the component form and find the norm of the vector with initial point P and terminal point Q. The first part is straightforward. We're starting at P and we're finishing at Q. So the formula that we want is Q minus P. Terminal point minus initial point. So I'm doing minus 5, 2, 2, minus 3, 4, 1. Do each of the coordinates separately. First, minus 5 minus 3 is the same as minus 5 plus 3, or minus 2. 2 minus 4 is minus 2, and 2 minus 1 is 1. So the component form of this vector is minus 2, minus 2, 1. And then we're asked to find the norm of this vector. The norm of v, we use our formula, square root of v1 squared plus v2 squared plus v3 squared. Put the numbers in, and the answer is 3. How can we visualize adding or subtracting vectors? We have 2 vectors, u and v. We can visualize adding them together in 2 different ways. First, look at the left picture. We might imagine that we put u and v nose to tail. In other words, the terminal point of u becomes the same as the initial point of v. And then u plus v is this green vector, which has the same initial point as u and the same terminal point as v. There's another way that we can think of adding 2 vectors together. We can imagine that u and v have the same initial point. We can draw this parallelogram, and then u plus v is the vector from the bottom left corner to the top right corner. We can multiply a vector by a number. Let's suppose we start with the red vector u, and then we multiply by a number. For example, 2u. 2u points in the same direction as u, but the length of 2u is double that of the length of u. 0.5u points in the same direction as u, but the length is a half of that of u. We can multiply by a negative number. For example, minus 2u. Minus 2u and 2u have the same length, but minus 2u points in the opposite direction. We can subtract two vectors, and there's two different ways to think about this. In the left picture, we can imagine that u and v have the same initial point, and then we can finish up this. We can draw the green vector which completes the triangle. This vector is u minus v. Or there's another way to think about this. We can draw u, and then at the terminal point of u, we can take the initial point of minus v. Remember, minus v has the same length as v, but points in the opposite direction. Then the green arrow is the vector u plus minus v. And of course, u plus minus v is exactly the same as u minus v. Let's suppose we have two vectors, u and v, and we have a number k. Remember, bold for vectors, bold u is a vector, u1, u2, u3, these are numbers. Bold v, v is a vector, v1, v2, v3, these are numbers, and k is a number. We can add up u plus v by adding up each component in the coordinate form. u1 plus v1, comma u2 plus v2, comma u3 plus v3. We can multiply u by the number k just by multiplying each coordinate by k. So ku1, ku2, ku3. Now note that the norm of ku1, in other words, the norm of ku1, ku2, ku3. We can calculate this using our formula for the norm. That, of course, is the same as the square root of ku1 all squared plus ku2 all squared plus ku3 all squared. Or the same as the square root of k squared u1 squared plus k2 squared u2 squared plus k2 squared u3 squared. The k2 we can factor out, and then we can break this square root into two square roots. The square root of k squared multiplied by the square root of u1 squared plus u2 squared plus u3 squared. But the square root of k squared is just the same as the absolute value of k. Think about this. If k is 3, k squared is 9, square root of 9 is 3, which is what we would get. If k was a negative number, let's say minus 3 squared is 9, square root of 9 is 3. We get the absolute value of minus 3 or plus 3. We get the absolute value of k multiplied by the norm of u. The formula to remember is the norm of ku is equal to the absolute value of k multiplied by the norm of u. And let me just point out, because k is a number, we use these single vertical lines. Because u is a vector, for the norm of u, we use double vertical lines. Ku is a number multiplied by a vector, that is a vector. As I said previously, the vector minus u has the same length as u, but points in the opposite direction. Let u be the vector minus 1, 3, 1, and v be the vector 4, 7, 0. Find 2u plus 3v, u minus v, and norm of a half u. First of all, let's do part A, 2u plus 3v, 2 multiplied by minus 1, 3, 1, plus 3 multiplied by 4, 7, 0. 2 multiplied by minus 1 is minus 2, 2 multiplied by 3 is 6, 2 multiplied by 1 is 2. Likewise, 3 multiplied by 470 must be 12, 21, 0. Add these numbers together, we get 10, 27, 2. Part B, I'll leave for you to check when you rewatch this or read the lecture notes. Let's move on to C. The norm of a half U. There's two different ways to calculate this. We could calculate a half U first, and then we could calculate the norm of the vector. Or we could use the method which I'm using here. We could remember that the norm of a half U is the same as a half multiplied by the norm of U, because a half is a positive number. We can calculate that the norm of U is square root of 11, so the norm of a half U is a half square root of 11. I'm going to go through some properties of these vector operations very quickly. On this slide, U, V, and W are vectors. A and B are numbers. U plus V is always the same as V plus U. It doesn't matter which order we add them together in. Likewise, U plus V plus W is the same as U plus V plus W. Same as for numbers, we can add them up in whichever order we wish. U plus the 0 vector, that's the vector 0, 0, or in 3 dimensions 0, 0, 0, of course is the same as U. U plus minus U is the 0 vector. For number 5, 0 on the right, which is written in bold, is the 0 vector. But the number on the left, just here, that's 0, which is not in bold, is just a number 0. This line says the number 0 multiplied by U is equal to the 0 vector. Moving on, the number 1 multiplied by U is equal to U. A multiplied by BU is the same as ABU. Multiply numbers and one vector together, doesn't matter which order we do them in. A, U plus V is the same as AU plus BV, as we would expect. And A plus B multiplied by U is AU plus BU. So far, everything is as we would expect. Something that we can't do is we can't multiply two vectors together. So we must never, never write UV. It doesn't mean anything. We can't do this. This notation would be meaningless. A vector U is called a unit vector if the norm of U is equal to 1. So for example, I'm saying that the vector 2 to the power of minus 1/2, 1/2 minus 1/2 is a unit vector. And we know it's a unit vector because if we calculate the norm of this, if we use our formula and we go through the calculation, we get 1. Unit vector means norm is equal to 1. If we're in 2 dimensions, there are 2 standard unit vectors, which are called I and J. I is the unit vector 1, 0, and J is the unit vector 0, 1. If we're in 3 dimensions, we need 3 standard unit vectors. And these are I, J, and K. Any vector in 3 dimensions can be written as a linear combination of I, J, and K. In other words, we can write that the vector V is number multiplied by I plus number multiplied by J plus number multiplied by K, where these numbers V1, V2, V3 are the numbers from the component form. In other words, two different ways to write the same vector. We could use bracket v1, v2, v3 bracket, or we could write v1i plus v2j plus v3k. You will see today and next week that sometimes I use the first form, sometimes I use the second form. If the norm of v is not equal to 0, in other words, if v is not the 0 vector, then v divided by the norm of v is always a unit vector. How do we know this? Because we can calculate the norm of v divided by the norm of v, which of course is just 1 divided by the norm of v multiplied by the norm of v, or 1. So what we have is two vectors which point in the same direction. Vector v and vector v divided by the norm of v are pointing in the same direction, but the length of this orange vector is equal to 1. We can use this trick to find a unit vector which is pointing in the same direction as any vector that we're given. Anytime we're given a vector v and we're asked to find a unit vector pointing in the same direction, we'll just take v and we will just divide by the norm of v. So for example, find a unit vector u which points in the same direction as the vector p1, p2. We're going to calculate p1, p2. We're going to calculate the norm of p1, p2. And then u is going to be p1, p2 divided by the norm of p1, p2. The vector p1, p2 is just p2 minus p1, always terminal point minus initial point. And you can check that this is 2i plus 2j minus k. I'm also going to leave it for you to check that the norm of this vector is equal to 3. As soon as we know this, we can calculate the vector that we asked for. The unit vector that we want is p1, p2 divided by the norm of p1, p2. And if we put these numbers in, we find that the unit vector that we were asked to find is 2/3 I plus 2/3 j minus 1/3 k. That's enough about vectors. How can we use vectors? We cannot multiply two vectors together, but we have another way of combining them, which is called the dot product. If we're in two dimensions in R squared, then the dot product of u and v is u1 v1 plus u2 v2. This is vector dot vector is equal to number. This is not multiplying two vectors together. This is taking the dot product of two vectors to find a number. In 3 dimensions, we have the same idea, but u dot v must be u1 v1 plus u2 v2 plus u3 v3. Using the dot product, we can calculate the angle between any two vectors. Look at this picture. Let's suppose we have two vectors, u and v, which I've drawn using the same initial point. And let's suppose the angle between these two vectors we call theta. Then we have a nice formula. This angle, theta, is inverse cosine of u dot v divided by the norm of u, norm of v. Let's look at some examples. Suppose we have two vectors, 1, -2, 1, and -6, 2, -3. And we want to calculate the dot product of these two vectors. First, we take the first two numbers, that's 1 and -6, and we multiply them together. And then we take the second numbers, -2 and 2, and we multiply them together. And then finally, we take the third numbers, -1 and -3, and we multiply them together. We get -6, -4, and 3. Add these numbers together, we get our dot product of -7. Or a half I plus 3j plus k dot 4i minus j plus 2k. I'll leave this for you to double check. This dot product is the number 1. Or perhaps we are asked to find the angle between two vectors u and v. We've seen the formula that we want. We want to use the formula, this angle is inverse cosine of u dot v divided by norm of u, norm of v. So what do we need? We need to calculate u dot v, we need to calculate the norm of u, and we need to calculate the norm of v, and then we're going to combine them together and take the inverse cosine. U dot v, I'm going to leave for you to check, is -4. I'm also going to leave for you to check that the norm of u is 3 and the norm of v is equal to 7. If we put these numbers in, we have -4 divided by 3 multiplied by 7, or 21. Take the inverse cosine of -4 over 21. We get approximately 1.76 radians, or 98.5 degrees. Another example. Let's suppose we're given 3 points A, B, and C, and we're asked to find the angle theta, shown in this picture. This is the angle ACB. That's the angle at C, between the lines AC and CB. What we need is two vectors. We need a vector here and a vector here. After we know these two vectors, we'll use the formula to calculate the angle between these two vectors. The angle that we want is the angle between the vector CA and the vector CB. So we calculate everything that we need first. The vector CA we can calculate as -5, -2. The vector CB we calculate as -2, 3. I'm going deliberately quickly because I'm expecting you to reread this and check that you're happy with this. The dot product of these two vectors is 4. The norm of the first vector is the square root of 29, and the norm of the second vector is square root of 13. Please check this for me later. After we have this information, we put these numbers into our formula. The angle that we want is inverse cosine of CA dot CB divided by norm of CA, norm of CB. And after we put the numbers in and calculate it, we get approximately 78.1 degrees. Two vectors u and v are called orthogonal if and only if their dot product is equal to the number 0. Now, remember the formula for the angle. The formula for the angle was that theta is equal to inverse cosine of u dot v divided by norm of u, norm of v. Because I'm writing with my mouse and underlining u. If we rearrange this formula, we get the formula u dot v is equal to norm of u, norm of v, cos theta. So that's where this comes from. What does this tell us? This tells us that u and v are orthogonal if and only if this number is equal to 0. How can we make this number 0? Either the norm of u is 0, in other words, u is the 0 vector, or the norm of v is 0, in other words, v is the 0 vector, or cos theta is 0. How do we get cos theta equal to 0? Cos theta is equal to 0 if theta is 90 degrees. So orthogonal means either one of the vectors is 0 or the angle between the vectors is 90 degrees. For example, the vector 3, -2 and 4, 6 are orthogonal because their dot product is equal to 0. Neither of these vectors are the 0 vector, so straight away we know the angle between these two vectors must be 90 degrees. Another example, 3i - 2j plus k and 2j plus 4k are orthogonal because their dot product is equal to 0. Again, neither of these vectors is the 0 vector, so the angle between these two vectors must be equal to 90 degrees. The 0 vector is orthogonal to every vector u because u 0 dot u is always equal to 0. Let's run through some properties of the dot product quickly. If we have two vectors and we're taking the dot product, it doesn't matter which order we do them in. U dot v is always the same as v dot u. If we have two vectors and a number k, again, it doesn't matter which order we do this calculation in. We could do ku first and then dot with v, or we could do u dot kv or k multiplied by u dot v, and we would always get the same answer. Rule of 3, u dotted with v plus w is the same as u dot v plus u dot w. U dot u is equal to the norm of u squared. Let's think about this. Let's suppose we're in 2 dimensions, just to make this easier for me to write. The norm of u is u1 squared plus u2 squared. So if we square this, norm of u squared is square root of u1 squared plus u2 squared, all squared, or u1 squared plus u2 squared. But of course this is exactly the same as u dotted with u. And rule number 5, which we've talked about on the previous slide, 0 vector dot u is the number 0. Again, this is a number, and this 0 written in bold is the 0 vector. Something which we're going to be talking about a lot in the future, next week or in 2 weeks' time, are projections. So let me talk about the first type of projection in this course now. We can project one vector onto another vector. First of all, just look at this picture which I've circled. Let's suppose we have these two vectors u and v, and let's suppose we want to squash u onto v. Just imagine that we push down from the top and we squash u straight downwards onto v. Then we get this new blue vector, which is called the projection of u onto v. There's another way to think about this. We could imagine that we're looking for the shadow of u. Let's suppose we have some sunlight or other light shining downwards, and we're looking for the shadow of u onto v. The shadow of u onto v is this blue vector. Precisely, the projection of u onto v is the vector from P to R. Now, so far I've been talking about two vectors where the angle between them is less than 90 degrees. Let's suppose instead we have two vectors where the angle between them is greater than 90 degrees. Then again, we want to squash u downwards onto a line passing through v. So again, we squash u downwards, or we take the shadow of u onto some sort of imaginary line which is passing along through v. And we get this blue vector. The projection of u onto v is this blue vector from P to R. We can create a formula for the projection of u onto v, because this is a length multiplied by a unit vector. It's the length of the vector multiplied by a unit vector pointing in the same direction. Or the norm of the projection of u onto v multiplied by, what's a unit vector pointing in the same direction as v? We've talked about this earlier. V divided by the norm of v is a unit vector pointing in the same direction as v. So what we need is the length of this projection. For this number, we go back and we look at this picture. Using trigonometry, the length of the blue side of this triangle must be norm of u cos theta. So this is what we put in. We have norm of u cos theta and then multiplied by our unit vector v divided by norm of v. Rearrange these terms. Norm of v cos theta divided by norm of v squared multiplied by v. But norm v cos theta is exactly the same as u dot v. So we get the formula that we're going to be using. The projection of u onto v is u dot v divided by norm of v squared v. This is an important formula, so we're going to write this as a theorem. When you go into an exam for this course, make sure you have formulas like this written down. The projection of u onto v is given by this formula. For example, the type of question I might ask you is, find the projection of this vector u onto this vector v. We have our formula. We're asked to calculate the projection of u onto v, so we need to calculate u dot v divided by the norm of v squared multiplied by v. I'm going to skip ahead. I'm going to leave this for you to check. If you put the numbers into this formula, the answer that you get is minus 4 over 9i plus 8 over 9j plus 8 over 9k. Again, please take the time to double check this calculation is correct when you rewatch these videos or when you read the lecture notes. Another example, find the projection of f onto v. We have our formula, f dot v divided by the norm of v squared multiplied by v. Put the numbers in. Please check that the answer is minus 1 over 10i plus 3 over 10j. Our final chapter for today is the cross product. This is another way to combine two vectors together. For the cross product, we're going to need to be using our left hand again. Let's suppose we have two vectors, u and v. Let's suppose we hold our hand, so our second finger points in the same direction as u, and our first finger points in the direction of v. Then our hand tells us which way u cross v points, because u cross v always then points in the same direction as our thumb. Let me be a little bit more precise. Let's suppose that n is a unit vector which satisfies three rules. Let's suppose that n is orthogonal to u. In other words, the angle between u and n is 90 degrees. And let's suppose n is also orthogonal to v. Angle between v and n is 90 degrees. And let's suppose that we choose the direction of n using our left hand rule. Go back to the picture. The angle between u and n must be 90 degrees. The angle between v and n must be 90 degrees. And we use our left hand to see that in this picture n points upwards. Then we can define the cross product of u and v. Cross product of u and v is norm of u multiplied by the norm of v multiplied by sine theta, where theta is the angle between u and v, multiplied by this unit vector n. Let me just remark before we go on, we have two ways to combine two vectors, two products. We have the dot product, u dot v, which gives us a number, and we have the cross product of u and v, which gives us a vector. We can say that two vectors u and v are parallel. Parallel means they point in the same direction, like this, or it means they point in opposite directions, like this. They're parallel if the angle between them is 0 degrees, and that means they point in the same direction, or 180 degrees. In other words, they point in the opposite direction. But sine of 0 is equal to 0, and sine of 180 degrees is also 0. So if they're parallel, then sine of theta must be 0. Therefore, u cross v must be 0. And remember, not the number 0, but the 0 vector. Some properties of the cross product very quickly. Let u, v, and w be vectors, let r and s be numbers. RU cross SV is the same as RS multiplied by U cross V. We can move the numbers around however we want, it doesn't matter. U cross V plus W is the same as U cross V plus U cross W, as we would expect. But then things start getting perhaps a little unusual. V cross U is not the same as U cross V in general, because V cross U is the same as minus U cross V. I'm going to explain why soon. V plus W cross U is V cross U plus V cross U. Sorry, V cross U plus W cross U, as we would expect. That one makes sense. 0 cross U is 0. Again, this makes sense to us because multiplied by a number should multiplied by 0 should be 0. We're happy with this. U cross V cross W is an unusual one. This is the same as U dot W multiplied by V minus U dot V multiplied by W. U dot W is a number, and U dot V is a number. So what we have is number V minus number W, which is okay. We can multiply a vector by a number, but we can't multiply a vector by a vector. Let's talk about property 3 first. Property 3 said that V dot U is the same as minus U cross V. Why is this true? In the left picture, I have U and V, and using my left hand, with U on the second finger, V on the first finger, N must point upwards. So U cross V must point upwards. Now let's suppose instead I want to have V on my second finger and U on my first finger. Then I have to turn my hand upside down to be able to do this. If I turn my hand upside down, now my thumb is pointing downwards. So V cross U must point downwards by the left hand rule. This is why V cross U is minus U cross V. U cross V and V cross U have the same length, but one points in the opposite direction from the other one. Using the cross product, we can calculate the area of a parallelogram. The area of a parallelogram is the length of the base multiplied by the height. The length of the base is easy. Here's the base. The length of the base is just the norm of U. What is the height? For the height, we use trigonometry to see that the height must be the norm of V multiplied by sine theta. The height of this parallelogram must be norm of V sine theta. But we know what this is. Norm of U, norm of V sine theta is just exactly the same as the norm of U cross V. Go back and look at the definition of U cross V, and then take the norm. The unit vector n disappears, and this is what we are left with. After we know the area of a parallelogram, we can calculate the area of a triangle, because as we can see from this picture, the area of this triangle is just half the area of a parallelogram. So we have a half norm of U cross V. This is a nice formula for the area of a triangle like this. Let's look at some examples. Sorry, we'll look at some examples later. First, I want to find a formula for U cross V in terms of the component form of U and the component form of V. First, we'll look at the standard unit vectors, I, J, and K. I points along the x-axis, J points along the y-axis, and K points along the z-axis. First thing to note is that I cross I must be 0, because the angle between I and I is 0, sine of 0 is 0. For the same reason, J cross J is 0 and K cross K is 0. What about I cross J? Here we go back to the picture. What is I cross J? We need to use our left hand. Hold our left hand up so that our second finger points in the same direction as I, and our first finger points in the same direction as J. And then we ask, which direction is our thumb pointing? And if you hold your hand up to the screen, use your left hand, you should see that your thumb is pointing in the same direction as K. So I cross J must point in the same direction as K. Well, norm of I is equal to 1, norm of J is equal to 1, sine 90 degrees is equal to 1, so I cross J must be just equal to K. As soon as we know this, we know that J cross I must point in the opposite direction, so it must be minus K. For the other 4, I'm going to leave it for you. Go back to the picture 2 slides before. Hold your left hand up to the screen. You should be able to check that J cross K is I, K cross J is minus I cross K is minus J, and K cross I is J. Now that we know these, we can calculate U cross V. I want to calculate U1I plus U2J plus U3K cross V1I plus V2J plus V3K. We have 3 terms cross 3 terms. First we do the first ones. U1, V1, and then I cross I. Then first one and second one. U1I cross V2J, or put the numbers first, U1, V2, and then I cross J. And then first one cross third one. U1, V, I cross K, and so on. You will see that because we have 3 terms cross 3 terms, 3 multiplied by 3 is 9. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Of course, some of these are 0. I cross I is 0. J cross J is 0, and K cross K is 0. Rearrange these. We have U2V3 minus U3V2I minus U1V3 minus U3V1J plus V1V2 minus U2V1K, which I'll leave for you to check, or you can just believe me and just believe me when I say this is the formula for U cross V. This is an important formula, so I'm going to write this as a theorem. Make sure you have this formula with you before you go into an exam. If U is U1i plus U2j plus U3k, and V is V1i plus V2j plus V3k. Then U cross V is given by this formula, which we've just calculated. Some of you may have studied matrices and determinants in high school. If this is true, then there's another formula for U cross V, which you can use if you want to. U cross V is given by this actually pseudo-determinant, or determinant of this pseudo-matrix, ijk V1, U1, U2, U3, V1, V2, V3. If you didn't study matrices at high school, then just ignore this formula. You don't need this. You can use the formula that I gave on the previous page. For example, find U cross V and V cross U if U is 2i plus j plus k and V is minus 4i plus 3j plus k. We have our formula. The formula is going to be something I minus something j plus something k. First, we have U2 V3. U2 is 1, and V3 is 1. So we have 1 multiplied by 1, or 1. And then we're going to be doing minus U3 V2, swapping the positions of 2 and 3. Where's U3? U3 is also 1. V2 is 3. So we have 1 multiplied by 3, or minus 3. And so on. I'll leave this for you to check. You can check that the correct answer is minus 2i minus 6j plus 10k. Next, we want V cross U. If we wanted, we could do the same calculation, but that would be wasting our time. It's quicker to just remember that V cross U is minus U cross V, or minus the vector we just found. For example, find a vector perpendicular to the plane which contains the point P, Q, and R. What we're going to do is we're going to calculate PQ, that's this angle, this vector. We're going to calculate PR. Both of these vectors are inside the plane. We want a vector which is orthogonal or perpendicular to the plane. So we want a vector which is orthogonal to PQ and orthogonal to PR. Now that's easy. We'll just take the cross product of PQ and PR, because PQ cross PR is always orthogonal to PQ, and PQ cross PR is always orthogonal to PR. So we calculate PQ. I'll leave this for you to check. We calculate PR. Again, I'll leave this for you to check. And then we take the cross product of these two vectors. Using the formula from the theorem, I will leave it for you to check. It's 6i plus 6k. Please pause the video if you're rewatching this, or if you're reading the lecture notes. Take the time to go through this calculation and check that this is correct. Next example, find the area of the triangle PQR. And this is the same PQ and R from the previous example. We already know PQ cross PR because we've just calculated in the previous example. We've just calculated that PQ cross PR is 6i plus 6k. We also have a formula for the area of a triangle. Area of the triangle is a half norm of PQ cross PR. So all we need to do is calculate a half of the norm of 6i plus 6k. And I'll leave it for you to check that the answer is 3 square root of 2. Find a unit vector perpendicular to the plane containing P, Q, and R. Same P, Q, and R as used previously. We've already found a vector which is perpendicular to the plane. Now we're asked to find a unit vector which is pointing in the same direction. We know how to find a unit vector which is pointing in the same direction as PQ cross PR. We just take this vector and we divide by its norm. All we're going to be doing is 6i plus 6k divided by the norm of PQ cross PR. You can check that the answer is 1 over root 2i plus 1 over root 2k. Is this a unit vector? Let's just check. What is the norm of 1 over root 2? 0, 1 over root 2. It's the square root of 1 over root 2 squared, or a half, plus 0 squared plus a half. That's square root of 1, or 1. Yes, this is a unit vector. It's often worth doing this quick check to make sure we haven't made a calculation. We're asked to find a unit vector. Is the answer that we give really a unit vector, or did we make a mistake? A triangle is inscribed or drawn inside a cube of size 2, as shown in this picture. Use the cross product to find the area of the triangle. If a question says use something, then you have to use this method. If you calculate the area using a different method, then you get 0 points because you didn't do what the question asked you to. If a question says use the cross product, then you must use the cross product. We need some vectors. We need 2 vectors, and then we can use our formula to find the area of this triangle. Before we can write down vectors, we need coordinates. So what I'm going to draw is I'm going to draw x, y, z axes on the cube. And we could draw this anywhere we want. I choose to draw these axes so that the origin is on the back corner of the cube. And then I can label the corners of the triangle. Point A must have the coordinates 2, 0, 0 because it's on the x-axis, and the distance from the origin is 2. Then we go 2 units along the y-axis direction to get to 2, 2, 0. And the vertex C, it's on the z-axis, must have coordinates 0, 0, 2. Now that we know coordinates for the corners, we can write down 2 vectors. I choose to use AB and AC. AB, we can check 2J. AC is minus 2I plus 2K. We need to calculate the cross product of these 2 vectors. AB cross AC. I'm going to skip talking about this. I'll leave this for you to double check when you go through this. Please check that the answer is 4i plus 4k. What is the area of the triangle? Our formula for the area of the triangle is half norm of AB cross AC. Put these numbers, these vectors, into our formula. I'll leave it for you to check that the area of this triangle is 2 root 2. one final idea. The triple scalar product of u, v, and w. And it's in this order. First u, then v, and then third w. The triple scalar product of u, v, and w in this order is u cross v dot w. What do we use this for? We can use this for the volume of a three-dimensional object called parallelepiped. This three-dimensional object which I've drawn, in which all of the 6 sides are parallelograms, is called a parallelepiped. The base of this shape is a parallelogram. We know the area of a parallelogram is norm of u cross v. For the height of our parallelepiped, we measure the angle theta between u cross v, which is a vertical line, vertical vector, and w. And then using trigonometry, the height must be norm of w cos theta. The volume is the area of the base multiplied by the height. We know these. The area of the base is u cross v, and the height is norm of w cos theta. But that's exactly the same as the absolute value of the triple scalar product. U cross v is a vector, w is a vector. Take the dot product of these, we get a number. Because we have a number, we use single vertical lines for the absolute value. One final comment before I finish. We can do the dot product in both 2 dimensions and in 3 dimensions. But for the cross product, we need to be able to hold up our left hand to determine the direction of u cross v. And we can't do this in 2 dimensions because our hand only exists in 3 dimensions. Because of this, we can only do the cross product in 3 dimensions. There is no cross product in 2 dimensions. And that is the end of today's lesson. Next week, we're going to be talking about lines in 3-dimensional space, planes in 3-dimensional space, and projections of one object onto another object. We're going to take the ideas of projecting a vector onto a projector from today, and then we're going to extend these ideas to things like projecting lines onto planes or vectors onto lines, things like this. It's now your chance to ask questions.